My name's Doug Hood. I work from Oracle. I'm going to be talking about times 10 velocity scale. It's in a memory database. So when I'm not talking to customers, doing proof of concepts or benchmarks, I do a lot of blogging at Scalable dbDoug. So what I want to talk today is about velocity scale, what we're doing in the cloud, give you a bunch of demos and questions. So just first of all, this is a very select bunch. How many of you have heard of times 10? Wow. How many of you use times 10? Interesting. Okay. So this is not the times 10 of 20 years ago. This is a very new and different thing. So times 10's been around for 20 years. There's over 1 billion customers using times 10 just from Ericsson. So if you look at telco stacks, times 10 is used in many different places. So we use it airlines, banks, all over the places. So this is, I'm very biased. I'm a product manager. I also am a developer. I wrote over 30,000 lines of C code for it, so I'm biased. This is something that Forrester put out recently. They've ranked times 10 in Oracle In Memory above HANA. There's a bunch of other names you've probably heard of. A lot of those companies are here today. The point is they were ranking Oracle as the top database for in-memory. So I just want to differentiate. We're talking about databases, not data grids, not data pipes, not data lakes. This is a database. So we just do traditional database stuff, but really fast. So got a few more people in. How many of you have used times 10? Just hands up, those new people. Okay, cool. So the point is, times 10 was the first commercial in-memory database, way back in 1998. So they've been doing it for a very long time. You probably don't hear the name very much because it's embedded in other people's products. So what I'm going to be focusing today is the new version of times 10, which is a scale-out, shared nothing version of times 10. So a lot of the things I'll talk about will sound really familiar. Hey, that sounds just like grid gain, or that sounds just like Hazelcast, or that sounds like Punakawa. It's because when you're doing stuff in memory, there's only so many ways of doing it. We did most of the stuff 20 years ago. So the point is, times 10 is a relational database. It uses SQL. It uses primary keys, foreign keys, sequences, materialized views, SQL stored procedures. It's a relational database. So if you're familiar with something like Oracle, it's very similar to that. We do everything in memory, and we have ACID transactions. So even though we do everything in memory to go really fast, we also persist things to disk. If something bad happens, the machine reboots, the machine catches on fire, you still need to be able to recover. It's very fast and it's highly available. So when I say fast, we measure SQL operations in times 10 in microseconds, not milliseconds. So this is about 4 years old, this benchmark. We're just doing SQL selects based on primary keys on literally 4-year-old hardware. It's Intel Xeons. We're doing it in under 2 microseconds. We're also doing updates in just over 5 microseconds. So this is just on one box, 4-year-old hardware. So because times 10 is in memory, the performance of your SQL operations are determined by how fast your CPU goes. The faster the gigahertz, the bigger the L3 cache, the faster things go. So this is literally running on 4-year-old hardware, running at 2.2 gigahertz. Bigger gigahertz goes faster, latency goes lower. It's a good thing. So with performance, there's 2 aspects. There's latency and there's throughput. If you've got really low latency, as a side effect, you get high throughput. Now I just want to qualify, this is talking about the existing times 10 product from basically 20 years ago. So on a 1U machine with 2 Intel sockets, we're doing over 5 million transactions per second just on one box. Okay? Times 10 can act as a standalone database, as a system of record, or it can act as a read-write cache for your Oracle database, be it Oracle, be it RAC, be it Exadata, be it Oracle sharding. So you can either have it as a standalone system of record or as a read-write cache. So here's an example where we were using the exact same workload, the exact same data, the exact same application on both Oracle database on its own and the Oracle database with times 10. So this Oracle database is going pretty fast. Almost all of the operations are taking less than 1 millisecond. But what we've got, so that's the blue, so that's the latency. And the red, we're using times 10 as a read-write cache in front of Oracle. So in this case, it's a Java JDBC application. The exact same code is used. So when you run the program, you pass in a parameter to run it against times 10 or Oracle. So the exact same code is being used. So times 10 has a lot lower latency than Oracle. As you can see, the speed up, is it 10 times faster? Is it 69 times faster? It completely depends on the operation. The point being, even when you've got an Oracle database with all of the data in the SGA in memory, so you can forget about how fast the disk is because you're not using disk. So even when all of the data is in an Oracle database, we can still go a lot faster. Our marketing term is times 10 times faster. It completely depends. It might be 2 times faster, it might be 50 times faster. The point is, it's faster. So that's the existing product. It's a database. 99% of our customers don't run times 10 as a database. They run it as a highly available system. They require 4 or 5 nines. And we've provided 4 nines availability for the last 20 years. So there's a lot of different configurations that you can use to do that. Most customers use an active standby type scenario. Some customers can also use active-active. So with active standby, your writes go to the active database. The reads, reads can go to either active or standby, but on the standby, you can only do reads. So that's very similar to how MySQL, a bunch of other databases do things. It's simple. You write on one system, it replicates to others. It's highly available. If something goes wrong, you can just switch the role of the database from active and standby. You can have up to 255 read-only subscribers. So it's a read scalable solution. We've been doing this for 20 years. Not interesting. What's interesting to us is how do you scale writes. That's a far harder problem. With a single active database, the rate at which you can write is limited by how fast that machine is, more specifically, how fast the persistent storage of that machine is. So what we've done is we've come up with a scale-out, shared nothing version of times 10. So instead of having a database, we have a distributed database that runs on many machines, it scales horizontally, but to a developer, to an application, it looks like one database. So we do write, so it's active-active. So you can do updates on the same record on many different places. It will automatically resolve that for you. So you don't need to care, am I writing to the active or the standby? You've got a bunch of nodes, you just do writes anywhere, and it will work. So we do that transactionally consistent with ACID transactions. So logically, it's a bunch of different machines. To the application, it looks like a single application. So that's easy to say, customers have been doing that, different database vendors have tried to do scale-out databases for the last 20 years. To make things scale for non-trivial applications is hard. Like if you just got, one table and you're doing, a single SQL operation, anyone can scale, that's easy. But if you've got really complicated data models with complicated transactions, to make that scale, you've got to be smart about it. And one of the grid gains guys the other day was saying, you need to be smart about that and you need to collocate your data. And he's exactly right. So if you've got a relational data model and you're joining, if you're joining those rows, those tables on those rows, if you're doing network hops, that's going to go really slow. Doesn't matter how fast your computer is, you'll be bounded by the round-trip time of your network. So what we've done is we've allowed you declaratively to collocate your data. So if you've got a master detail type relationship, in this case we've got customers and orders. A customer can have 0 or more orders. For a given customer, if all of their orders were on the same machine, when you do a join, we can do that in memory. Because if those orders were on 1 or more machines, that would go a whole lot slower. So that primary foreign key relationship, we can collocate that. Likewise, if you've got some tables that are just used by everyone, you can have duplicate copies of that on every single machine. So the trick is to collocate data to minimize the number of network hops. But more importantly, do that transparently such that the application doesn't have to do anything. So I'm going to show you how we do that, but the point is existing application code will just work without knowing that it's a distributed database. So here's some examples, create table statements. The stuff in red is the new stuff. By default, you can distribute on the primary key. We do distribute by hash, it's a consistent hash. If you don't have that extra clause in the create table statement, it will by default create that distribution by hash. It turns out you don't actually have to distribute by the primary key. It can be any set of columns that you care about. Okay, so that's for the driving table, distribute by hash. That way you'll get an even distribution of data across your grid, no matter how big your grid is. To have the collocation for the foreign keys, we do distribute by reference. So you can have as many foreign keys as you want. You're going to choose one of those to collocate. So we're saying there, distribute by reference, and you're just naming the foreign key. And when you want to copy the data everywhere, you just add the keyword duplicate at the end of your table. So these are things that are done at the create table or alter table statement. So it's something the DBA does for performance tuning. The developer, the application, doesn't know or care. So I've talked about distributing based on the table. When you've got a wide table and many different access patterns, it may be that people are doing queries on columns or sets of columns that aren't part of the distribution. That'll still work, but it won't be optimal performance. To enable that, we support global secondary indexes and materialized views. So if you know what a materialized view is, we're saying, hey, let's have that set of columns and distribute it another way. So developers query tables. They can explicitly reference the materialized views, but if they don't, and the columns they're querying are included by the materialized view, it's just going to automatically work because that's what cost-based optimizers do in SQL databases. So developers do SQL, and we worry about how to make that go fast under the covers. So times 10 velocity scale is optimized for OLTP. So we do ACID transactions, standard stuff, commit, rollback. Readers don't block writers, writers don't block readers. We've got version control. We've got range and hash indexes, global secondary indexes. But by the way, we also do analytics. So any of you guys do analytics? Yeah. So, there's some of the syntax there. We support the with, we stole all the syntax from the Oracle database. So it's the same syntax, the same semantics, it just goes a bunch faster. So with, cubes, roll-up, grouping sets, a whole bunch of those things just work. So if you look at the Oracle documentation, that's how it works for velocity scale. So because you've got many nodes, if you're processing stuff with big group buys or order buys, that all goes in parallel for you. You don't do anything. You write. You use 20-year-old SQL, and it's going to go in parallel for you for free. So we're an OLTP database. I was doing some TPCH benchmarks recently. I'd like to say we're the fastest. We're not. I believe we're the third fastest. So, I mean, that's a lot faster than the Microsofts, the DB2s, the SQL servers. But the fact that we can do it and the fact we can go really fast is just by the way. We're focused on OLTP. So we've talked a little bit about the fact it's a relational database. It uses SQL. How the SQL works is transparent to the developer. But that's only part of the story. If you've got a distributed database spread over many nodes and it's shared nothing, if one of those machines goes down, be it temporarily, or if it catches on fire, that would be a problem because your database has been chopped up into these different chunks. So to get around that, we provide high availability via case safety. That's not something we invented. Lots of people use it. It just means you have multiple copies of that same chunk of data. So some customers use shards. These are like shards. They act like shards. The difference is with a sharding database, normally the SQL is crippled. There's certain things you can't do. You have to pass in the shard key. Normally, to get around, because of the way databases have been designed with sharding, they've limited what the SQL is. We've put a lot of engineering in such that we have logically sharded, but you can still use the same SQL unchanged. So the point is, we have multiple copies. So logically, you've got a fully connected mesh. In practice, you have sets of machines. Is it 2 copies? Is it more copies? It just comes down to how paranoid you are. So all of these copies are active-active. So if you do a write on the left or a write on the right at the same time, it'll just work. So we've got a distributed lock manager. We just make all the difficult stuff work for you such that the developer doesn't need to do that. So we're doing ACID transactions, so we've emphasized having strong consistency. Some NoSQL databases say, it'll be eventually consistent. Figure that out. If you've got lots of users and lots of changes, how can you ever know whether things are correct or not? You can't. So we've got ACID transactions, so whether it was one database or many, it has the same semantics. So we're focused on the consistency. So you can initiate transactions anywhere, it'll just work. And queries can span any and all of the machines. So you connect to your favorite machine or a random machine, we don't care. That's up to you. So what happens if something goes wrong? Say you're having a bad day and half your machines are down. Everything is still going to work because we've got at least one copy of the data. Like half of my A's went down, don't care. Half of the B's went down, don't care, because I've got at least a copy of A, B, C, and D. So that's assuming we'd arbitrarily chop the database into 4. We could chop it into 50. That's literally how many machines you need. If you're having a really bad day and both of the copies go down, that gets interesting. We believe the behavior of this is determined by the application. Some applications will say, whoa, stop, the earth is, the sky is falling. And some applications will say, I don't care, let's keep going with the data you've got. So it depends on the application which is the right behavior. So we give the developer the choice at runtime to determine what that behavior is. So if you don't care, you can keep going. If you do care and those machines can't be recovered quickly, at that point you'd need to recover from backup. So just having a distributed database is interesting, but it's only part of the story. What say, it's month end, you need to add more machines? Or what say some machines die? Or what say you want to, update the operating system or put in a new version? You need to be able to dynamically grow and shrink the grid, the distributed database on the fly. So in this example, instead of having the database split in 4, we're having it split in 5. We've added some more machines, and then when it's a good time, you can redistribute that data. So you need to be able to do that on the fly. Grow it or shrink it as needed. So here's just some bottlenecks. There's a lot of different bottlenecks. lies, damn lies, benchmarks, whatever. What we've done is we've tried to look at things that are interesting. So last year, Google put out a benchmark, and they said, we're the best. They did this benchmark, and they said, we're better than Amazon Aurora, and we're better than MySQL. So they tuned the hell out of their database, and they ran it on Google Cloud. And they paid a lot of money to do the equivalent on Aurora using AWS. So they said, we're the best. And almost immediately, the Amazon people said, you didn't tune that very well. And they reran the benchmark, and turned out Aurora was slightly different, slightly better. And I said, thank you. I don't want to spend a lot of money on Google Cloud or Aurora Cloud, and I'm not going to pretend that I'm the expert at doing those systems. Google said, this is the fastest way of doing it. Amazon said, this is the fastest way of doing it. So I said, thank you. You've defined the workload. You've defined the VM size. You've defined the amount of concurrency. You've defined the amount of data. Why don't I just copy that result on the Oracle Cloud, and then we'll have an apples-to-apples comparison. So in this scenario, it's doing synchronous replication between data centers. So are they called availability zones? Are they called availability domains? Depends on your cloud. In reality, you've got two different data centers, and you're doing synchronous replication. So synchronous replication is the slowest way to do things. If you do it async, it goes really fast. So this is the worst possible case. You're doing synchronous replication. You've got VMs with 16 cores, and you've got 32 client threads. So this is using Sysbench, which is a 10-year-old OLTP benchmark. Download it. Anyone can use it. So it's a client-server benchmark. So on exactly the same environment, on this benchmark, which is bottlenecked by the round-trip time between data centers, we were roughly twice as fast as the competition. That's throughput, latency, a whole lot better. So even though we can do stuff in microseconds, if you're spending your time doing network hops, because that's what the benchmark defines, it doesn't help you that much. The point being, we were comparing apples to apples with these other guys. So that was one benchmark. Here's another benchmark. This is a workload that we've shipped with our product for over 10 years. So it's called TPTPM. What we're doing is transactions. We're doing update transactions, or we're doing select transactions. And we used 64 machines, because that's what they gave us, and we got just over 144 million transactions per second. And we looked at that number and said, that's not very good. Where is the bottleneck? It turned out the bottleneck was writing to disk. So we're doing ACID transactions. We're writing and committing and durably persisting those transactions. So writing to disk was the bottleneck. So we thought, why don't we rerun that benchmark without the writes? Just make it a read-only benchmark. 1.2 billion reads per second. So these are primary key lookups. So even though it says 64, we were using 64 instances of the database, but we only needed to run it on 32 machines. We used 64. For the read-write, there was a database per machine. For the read-only, we had 2 databases per machine, because for the writes, we needed the extra machines with the extra local disk just to go there. So the point being, 1.2 billion primary key selects per second on 32 machines. And once again, these aren't even the fastest machines. These are Broadwells. These aren't Skylakes. They're running at 2.3 gigahertz. So you can scale out horizontally. We've got literally linear scalability. Add more machines, it goes faster. So times 10's been around for 20 odd years. Velocity scale, we're about to release it. We've gone through 3 rounds of beta. So we've finished the beta program. We're just about to launch the product. These are just some quotes from customers. This is from a South Korean company called Yilan, which you've probably never heard of. What was interesting was they were an existing times 10 customer. They took their existing times 10 schema and application, ran it on a velocity scale. And what they were saying was, within an hour, they had it up and running with no change to their codal schema. So that was one of our design goals. It's easy to make a new thing, but if you've got a new thing that nothing works for it, that's a challenge because you've got to figure out how to use it. So our design constraint was make it compatible with the old stuff. So that was Yilan, South Korean. Here's another South Korean company you might have heard of from, Samsung. They liked it. There's another company called China Mobile. China Mobile's kind of big. Just one province in China Mobile called Guangdong has got more subscribers than all of the US. So they're a big customer of ours, and they're very happy to use this stuff in the future. So just looking at time. So I've got some demos. Just any questions so far? You've been, yep.
Yes. Is it a general shared nothing architecture? So I'm wondering that how you make sure that it follows the ASIC property because you actually don't have a master to ensure
Yep.
the associated cross.
Yep, great question. And a really simple answer. We use two-phase commits. So that's a well-defined protocol. We optimize the hell out of the protocol, but the answer is we use two-phase commits. So whether it's two participants or many, doesn't matter. If everyone's ready, we acknowledge, and that's committed. If anybody says we're not happy, we roll it back. So that's how we do it.
All the other master lists, I think they claim to use two-phase commit also, but still eventual consistency. I think you tweak it.
Right, so I want to be really clear. There's lots of other databases out there that solve similar problems. And how good or bad they are, I don't care. So if they do it well, great. If they do it badly, that's their problem. So I don't want to be judged on how they do it. We use two-phase commits, we have ACID transactions, we have strong consistency. So like we've done some YCSB benchmarks, against the Cassandras, the Mongos, the Couchbase. We believe we can do as fast or faster NoSQL operations than those NoSQL databases can do their native operations. So they got rid of SQL, got rid of strong consistency, don't do ACID transactions to go faster into scale. We kind of like ACID transactions and relational databases because that's where we came from, but we just architected it such that we do it fast. So if you can keep your strong consistency and scale out horizontally and have lower latency, so if you can do it faster and scale better, we think that's a better answer. It took us a long time to do it because if you have eventual consistency, it's a really easy problem. To keep consistency, to work with primary and foreign keys, to be backwards compatible is a far harder problem. So it took us quite a few years to figure that out. So that was our approach. So long answer, we have ACID transactions because we do two-phase commits. I think you had a question?
Regarding memory consumption, for example, usually the data in memory, the size of the data is much bigger than in traditional Oracle database when it's stored in the disk. So what is the ratio? For example, if you have just regular Oracle database, let's say 1 terabyte of data, right, and you move it, this relational database, you move it to times 10. So how much memory it would consume?
Yeah. So I can give you a marketing answer or an engineering answer. The answer is it depends. Different data types take up different amount of space. We have a tool, TT size, you run it, it tells you exactly how much. Beyond that, it depends on the data type.
Right, but usually it's like twice bigger, 3 times bigger, 10 times bigger.
Or sometimes it's exactly the same space. It depends. So it's just saying which is longer. It depends.
To ask a similar follow-up question is that I know that in Oracle you define a system memory, right? And then they figure out that what actually should be in automatically on their own, so you don't do anything afterwards. So I think its content is identical to that approach, that where you set up what memory you
I want to be really clear on this. With the times 10 in memory database, the existing product, all of the data is in memory all of the time. if you're doing read-write caching, the working set is in memory. So say you had gigabytes of memory, you could be caching terabytes, which gets dynamically loaded. So that's the existing product. With velocity scale, all of the data is memory all of the time. So if you have a big database, pick your favorite hardware. You know, is it Dell, is it HP, is it Sun, is it Levino? I don't care. Pick your favorite hardware, which has however much memory, divide your desired database size by the memory of that machine, and that will give you how many machines you need. So because you scale out horizontally, how efficient the memory is or isn't doesn't really matter. Just add more machines. Adding more machines gives you more throughput, more availability, more connections. More is better. Okay, any other questions? Okay. Right, I'll show you some demos. So in this scenario, we're going to induce a failure and see what happens. So we're showing you in PowerPoint what happens, so you know conceptually what it is, and then we're going to show you for real. So when we tried to show these failures, it was a real challenge because the system automatically fixes itself, and it was fixing itself sub-second, so it was really hard to show it. So we've broken things down, because like if you do a kill -9 on a process, it's just going to automatically get refixed. So we got demons looking after demons. So it's healing. So what we've done is we turned things off and waited, and then turned it back on later, just so you can see cause and effect. So what we've got here is a database logically broken into 4, and we've got 2 copies. And we've got applications writing to it, and everything is good. Bear with me, this is a little movie. So, if we do something bad and turn off one of these machines, so we did an operation to stop it so it's not going to automatically come back. If that happens, your connections, your client-server connections are going to break, and they will automatically fail over to other machines. When we turn the machine back on, it'll automatically start talking to the rest of the grid, and new connections can be added. So the point was, things broke, we've lost, we've got 8 machines, we're down to 7 now, so the throughput's going to drop off. When we turn it back on again, people can reconnect again. So you're going to get a dip, and then things are going to come back. So what we've got here is just a very simple user interface to query what's going on at runtime. Very minor workload. It's doing 127,000 transactions per second. It's a relatively heavy workload. Each transaction is doing many operations. Something bad happens. The performance drops off. And then it jumps back up again because things can reconnect to the existing 7 remaining systems. If we then let it recover and then reconnect, things jump back up. So we turned that system off for many, many seconds to show that effect. If we didn't deliberately do it, it would just recover itself. So the point is, will self-heal itself. The developer doesn't need to do anything. The DBA doesn't need to do anything. So just do nothing, it'll fix itself. So that was one very quick demo. The next demo, using SQL Developer. So you can monitor and manage ×10 from the command line through SQL Developer or DB Console. I'm just doing SQL Developer because it looks cool. Via the command line, because we've got a whole bunch of machines, we need to be able to make changes, and we need to do it securely. Under the covers, we're using SSH and SCP. Things like SQL Developer or the DB Console are just doing that for you. So in this case, I've got a data model, primary foreign keys, some duplicates, all those different distribution clauses we've got. So if you're familiar with SQL Developer, we've enhanced that. In version 17.2 or later, this stuff is in there. At runtime is checking the version of velocity scale. So even if you got 17.2, you won't see this until you connect to SQL Developer. So the point is, in this table here, each row represents one of those machines where times 10 is running on. So everything's good, everything's up. If we look at the topology, we've got those pairs of machines for high availability reasons. So if you're familiar with SQL Developer, it looks just like an Oracle database. The SQL, you can see that new syntax, distribute by hash. So this is looking at how the data is distributed. If the data is evenly distributed, life is good. If you have a lot of skew, it won't be as fast and it's harder to do capacity planning. So if you've got roughly the same amount of data everywhere, so you can see all of those are within 1%. The exact numbers aren't the same because there's no such thing as a perfect hash. So it just needs to be close enough. We believe that if you're within 2%, it's going to be good enough. So the point is, you're seeing the percentage, you're seeing the numbers, and you're seeing the histograms. If it's all about the same, you know life is good. And you've got 6 bars because we've got 3 sets of 2 databases. So what we're going to do is a couple of things. So that was the accounts table. We look at the, so the accounts has got lots of foreign keys there. We've got the distribute by reference. And for the one we were duplicating, it's just the syntax duplicate. So that was just showing what we've got. With the duplicate, you're always going to have the same number of rows by definition. So the SQL, we support the 20-year-old SQL, the Oracle SQL with the, the left outer join syntax. We also support the, the newer ANSI SQL. You can use either, we don't care. The point being, even though it's a distributed database and it's got those different distribution clauses, the developer, the application doesn't know or care. So literally 20-year-old SQL is still going to work. So the point is, you connect to any one of those machines and the SQL just works. So we're getting a result set. In this case, there was 502 rows. If we connect to another machine, rerun the same query, we're going to get the same answer, which is kind of what you want. It doesn't matter who you connect to, you get the same answer. If the data doesn't change, you want to see the same answer. So what if something bad happens? If you're familiar with Oracle, if you do a shutdown abort or a kill -9, things are going down in a heap. So we did that on purpose just to show a failure. So we can see that things are down. So because we had copies of the data, so we can see we're missing the green copy. It's saying it's unavailable. When we rerun the query, it just works because there's still a copy of that data. So the program didn't change, the developer didn't do anything, it just works. So we talked before about elastic scalability. Let's add some more machines. So we've got a wizard, you type in a few values. The net effect is you get more machines. So we've added the machines, but we haven't redistributed the data. Let's tell it to redistribute the data. So like whether you're doing this through SQL Developer, whether you're doing it from the command line, whether you're doing it in DB console, whether you're doing it via REST calls, we don't care. The same operations occur, we're just showing you what it looks like graphically. So instead of having 3 copies, we now got 4, 3 things with copies, we now got 4 things with copies. So we've got this new blue bar, because it's more copies. So instead of having a third each, they've now got a quarter each. We rerun the same query, and we get the same answer. Kind of what you expect. So what we try and do is give you no surprises. We want you to have the same experience as a developer, as an application, as if it was one database, even though it's many. So it's relational, it's transactional, it's scale out. As you could see, the 144 million transactions per second with 64 machines or 1.2 billion reads per second. So it goes really fast. We believe it's faster than all other databases. So I come from Oracle. We believe this is faster than Exadata. We've benchmarked that. So it's fast, it's simple. So the product will work on-prem or in the cloud. We don't care. That's your deployment option. So just give you a quick sneak peek at that. So technically, the requirements are pretty minimal. On times 10, we run on AIX and HPUX and Windows and Linux and all sorts of weird platforms. The whole point of a scale-out shared nothing solution is it should go really fast on commodity hardware. We believe today that commodity hardware is x86 64. We don't care whether it comes from Intel or AMD. So we're just focusing on Linux because we believe that's what people are using. So if you've got 64-bit Linux, technically we only rely on glibc 212 or later. So what that means in practice is Red Hat 6.4 or later, 7 or later. Works on Ubuntu 14.04, it's ancient. Works on SUSE. We require TCP/IP or IP over InfiniBand. We require a file system, we don't care what it is, and enough DRAM for your database. So that's your unit. Have lots of those. So what that means is in practice is the common distributions is just going to work out of the box. So unlike older versions of times 10 where we had complicated installers, this is just a gzip tarball. You copy it over, you unzip it, boom. So whether you're running on bare metal machines, whether you're running on your favorite VM hypervisor, whether you're running on OpenStack, whether you're running on your favorite containers, we don't care. It's just Linux, it just works. So we're seeing a lot of our customers running OpenStack. So some of them use their own favorite cloud, like the Federal Reserve is running the stuff on AWS. Wasn't our choice, that's what they wanted to do. A lot of our customers say, for whatever business reasons, they want to keep it on-prem, but they're using OpenStack as their own private cloud. This stuff just works. So I've run this on Google Cloud, Azure, AWS. There isn't something I haven't come across this that just works. So whether you run it on-prem or in your favorite cloud, it's going to work. As the cloud product manager, what we're working on is a fully managed service in the Oracle Cloud. So instead of you being DBAs and DevOps, you say how much and how fast, and we provide that as a service. So you don't have to worry about how to configure it and patch it and manage it. We do that for you. So the things like provisioning it, scaling it, backing it up and restore, patching, doing upgrades, those are all services that we provide, be it point and click or you run a REST API. So whether you do all this yourself on-prem in your favorite private cloud and your favorite public cloud, you can do it, or with this new service, we'll do it for you, you rent it. You pay so much per month or per hour. So it's just a choice. So here's just some screenshots of what we're doing. This is functional. Hopefully the screens are going to look prettier by the time we ship it. The point is, it's a wizard. You type in some stuff you want. Basically, what's your email? Do you want to be charged per hour or per month? You're putting in your details, This is running on compute nodes. We give you, tell us your SSH key so that you can go in there and do stuff yourself. You can run your direct linked applications on it. You want to back up to object storage, give us those credentials. So that's, the backups are in your tenancy. You own the backups. We're just saying, give us the credentials so that we can create them and back up and restore. So we're just asking these metadata things. How big is that shape? If it's a small shape, it's going to be cheaper, but it's not going to go as fast. If it's a big shape, it's going to go faster. You're choosing that based on your capacity requirements. You say, we're ready to go, create it. Once it's done, you then got a UI. So you can do everything from the UI, or you can do it all from REST calls. That's your choice. The point being standard monitoring and management type things. So if you're familiar with Enterprise Manager, it's that sort of experience. So we can see, you know, we're looking at the perm and temp space. We can drill down on that stuff. We can see things like for each instance where things are, what's happening. For each of the components, the idea is you just do nothing, it works. It's automatic, but you still have manual override if you think you know better. Like EM, you can set thresholds and alerts. You know, if something is over some threshold, do this. What is do this? Is it email me? Is it run the script? It's whatever your DevOps type people want to do. Also, you don't have to, as a DBA, do stuff on the command line. You can do it all from the UI. You can all do it from REST. So basically, any operations you could do, we're enabling that in the UI. So, got 4 minutes left. So just to summarize, velocity scale is a new thing that's about to be released. It's a relational database. It runs in memory. It's scale out, and it's shared nothing. We believe it's the fastest OLTP database. We have data location transparency. Where the data is, the developer doesn't need to know. You just do SQL and it figures it out. If you want to know, we give you APIs to allow you to do that. It's just SQL. You can elastically grow and sync your grid. We've tried to make it as easy as possible to deploy and manage. We're focused on OLTP workloads. We also work for analytics. Run it on-prem in your favorite cloud. So, questions?
So this is in beta, right? So is it possible we can try? What is the option for trying?
Yeah, we've actually finished the beta program because we want to ship it GA. When we ship it GA, you can download it from OTN. So if you've got some more urgent need than that, you can talk to me afterwards. Was there a question? Okay. Any other questions? Thank you for your time.